Hello everyone. Let us begin today, and let me know if you cannot hear me. Okay, so last time we started talking about probability density functions. Today we will give few more examples of probability density functions. From the last lecture, we know that any function which satisfies these three properties, so it's always non-negative, continuous, and integration is equal to 1, that could be treated as probability density function. Some of the widely used probability density functions are the first one is uniform distribution. We write that X follows uniform distribution in the interval A to B, and the PDF of this distribution, the probability density function, is given by Fx x, which is 1 over b minus a, 1 over x is between a and b. The graph of this PDF looks like this. From the very first lecture about PDF. So this was the first example that we gave about the probability density functions. Somewhere in the beginning, like this one, example 1. Yeah. Okay. The second one in the list is distribution. These are basically different examples of probability density functions. So let's say x follows exponential lambda. Okay. And so this lambda is a parameter. The PDF here is given by Fx x is equal to lambda e to the power negative lambda x, and x is positive. The graph of this looks like. So if you look at the final example that we gave in the previous test lecture, which is this one, this was actually this random variable y was actually an exponential distribution with parameter 10, I guess. Yeah. So the PDF was 10 e to the power 10t, and therefore it is exponential 10 if you match with this PDF. So these are all different types of probability models. These are not the only ones, but these are very widely used probability density functions. Number C is normal Gaussian distribution. we write that x follows normal mu sigma square. So we read this as this one is mu and this one is sigma square. This mu and sigma and sigma are parameters. Mu can be anything, so mu can be any real number. Sigma is a positive parameter. The PDF here is given by fx x, which is 1 over sigma square root 2 pi e to the power negative 1/2 x minus mu over sigma whole square. And this PDF is valid for the whole real line. The x could be anything. The graph of this probability density function would look like this.
So please again read out the
Yes.
formula.
The formula is 1 over sigma square root of 2 pi. And this is pi. 1 over sigma square root of 2 pi e to the power negative 1/2 x minus mu over sigma whole square. So we have this mu and sigma. You have mu and sigma, so x minus mu over sigma square. Okay.
Sir, pi is in the under root portion.
Yes, yes.
Okay, sir.
It is inside that square root. Okay. All right. The fourth widely used probability density function is chi-square distribution. So I'm not using the notation x because x and chi looks similar. So let me write y. So y follows chi-square with n degrees of freedom. Okay. So we read this as so read as chi-square with n degrees of freedom. Okay, and the PDF of this distribution is given by f y, literally y, 1 over 2 to the power n over 2 to the power n over 2 gamma gamma n over 2. So I will tell about what this gamma function is. E to the power negative y over 2, y to the power n over 2 minus 1. And the graph of this looks like something like this. Okay, so let me tell you something about this gamma function. Okay, gamma
Sir?
of yes.
So excuse me, for that, for the previous graph you drawn for the chi-square distribution, you drawn that the graph from the first part is increasing, then it is reaching a peak, and then it is decreasing. So the
Right.
decreasing nature, sir, is it how it will be? That is that there is too much concave, or that is so much steepness or little steepness. Is it depending on the any y or like that one?
Yeah, it depends on this power shape.
Okay, sir.
Yeah, but my drawing is not so accurate. I think it is actually very smooth. It is not something like that. And also this location where it is taking maximum depends on this what. Okay. So this okay, what is this gamma function? This gamma of any quantity, let's say like gamma of n, is actually integration of this function e to the power negative x to the power n minus 1 dx. Okay, whenever n is positive. So it's difficult to evaluate this integration, but in some cases we can do. For example, gamma 1 is simply going to be 1, which is simply integration with negative x. Gamma of 1 half is square root of pi. There is a way to do this. And third property, gamma of n is n minus 1 times gamma of n minus 1. Okay, if as long as this n minus 1 is positive. So for example, if I see what is the value of gamma 3 half, by the last formula, gamma 3 half is going to be 3 half minus 1, which is 1 half, times gamma of 3 half minus 1, which is gamma 1 half, that is 1 half square root of pi. Okay. So for example, if you are doing chi-square with 3 degrees of freedom, you will have gamma 3 half. So gamma 3 half is going to be this quantity times. Or maybe if you're doing chi-square with 8 degrees of freedom, say like you have gamma 4. Gamma 4 is going to be, again from the last formula, is going to be 3 times gamma 3. Recursively, this is 3 times. Gamma 3 can also be written as 2 times gamma 2, which can also be written as 3 times 2 times gamma 2 is again 1 times gamma 1, and gamma 1 is 1. Gamma 1 is 1. So this is going to be simply 3 factorial, and so on. So just to give you one illustration of the gamma function. Okay. So this is about the chi-square distribution. Okay, so as I was saying, these are 4 widely used probability density functions. These are by no means like a complete class of probability density function. The complete zero probability density function is huge. There are so many different types of probability density functions. As you can realize that any function which satisfies these 3 properties, that integration is 1, continuous, non-negative, can be treated as a probability density function. And I just wanted to give you four widely used probability density functions. Obviously, there are many more functions which are not one of these groups. Okay, so does anyone have any question after that? So if not, I will move to the next topic, which is about the jointly distributed random variables. So today I will have time to cover the discrete case only. And the next lecture I will do continuous for the PDF. So let's start with an example. So example 1. Okay. What you do, you roll a dice and let n, excuse me, let n be the face value of the outcome. And then what you do, you toss a coin that n many times. I think I did this example in a different context last time. So then what you do, toss a coin n times. Let x be the number of heads. And you want to find the joint probability mass function, PMF, of this nx. I have not defined what a joint probability mass function is. I will define through this example. But the scenario is this: you toss a coin. Suppose the outcome is, let's say, like 4, and then you roll a dice. Suppose the outcome is 4, and then you toss a coin 4 times, and then you count the number of heads. Okay. So before I go into the solution of this thing, let me tell you a few points about this random variables. First of all, you can think of this nx. Okay, nx can be thought of as two-dimensional random vector. Or a two-dimensional random variable, or a random variable in two dimensions. So in the original definition of random variable, I was saying that it's a mapping from sample space to real numbers. But if you have a tuple like x, y, z, then that random vector is going to take values in R3. So it's not going to be a real number. It's going to be something in two dimensions. Okay. Other thing is that, so possible values that nx can take nx can take are so I have to use my pen here. Let's say for n, n is going to be, the lowest value is 1. When you roll a dice, the lowest you can say is 1. So 1 less than equal to n, less than equal to 6. Once you get the value of n, the number of heads can be at least 0, so no heads. So x is bigger than equal to 0, and at most it is equal to n. So this is a very important step here. Number of heads can be at most n. Right? So if you toss a coin n many times, so this n is itself a random number, you can get at most n many heads. If I try to draw a picture of this, it's going to be a very interesting looking picture. So let me draw this. Okay. Suppose this is the direction of n, that is the direction of x. Um, let's put the points. This is 1, 2, 3, 4, 5, 6. So the value of n, which is the face value, can be 1, 2, 3, 4, 5, 6. Now, if the face value is 1, the number of heads could be 0. So on this vertical line also, let me do 1, 2, 3, 4. So number of heads you could get is 0, or at most 1 head if you toss a coin once. If you toss a coin twice, you can get 0 heads, 1 head, or at most 2 heads. So if you toss a coin 3 times, which means the face value of the dice outcome is 3. 0 head, 1 heads, 2 head, or 3 heads. So this is let's select 3. If you toss a coin 4 times, 0, 1, 2, 3, 4, toss a coin 5, get 0, 1, 2, 3, 4, 5 heads. Okay. And for 6 tosses, you get these many heads. In fact, if I try to draw a virtual line joining these points, you know very well that equation of this line is going to be x is equal to n. So the whole point is that there are these possible outcomes. So there are these possible outcomes. If you get 4 as the face value of the dice roll, you toss a coin, you get 0, 1, 2, 3, 4 minutes. Equivalently, actually, you can write this as this range that I wrote there, 1 less than equal to n less than equal to 6. This can be written in a different way, which is if I do x first, so 0 less than equal to x less than equal to 6. Or suppose I choose x first, so x can be from 0 to 6. And for any fixed x, suppose like 3, n can run from 3 up to 6 for any fixed x. So if it is 3, n can be from 3 to 6. If x is 2, n can be from 2 to 6. If x is 1, n can be from 1 to 6. If x is 4, n can be from 4 to 6. Okay. So essentially, if I take x first, the possible range of n is going to be at most 6, and lowest is x. But there is a catch here. So if x is 0, x could be also 0. Okay, so if x is 1, n can start from 1 to 6. If x is 2, n can be from 2 to 6. If x is 1, n from 1 to 6. But if x is 0, even then n is from 1 to 6. N cannot be from 6, because if you roll a dice, the face value is at least 1. It cannot be 0. So n starting point of n is usually x, but it is never 0. So even if x is 0. So the way I would write it is it's going to maximum of 1 and x. Okay. So it is typically starting from the value of x, the range of n is starting from value of x is 0, and then also it is starting from 1. So that's why I write it from 1 to x. Anyway, the point is that so this is actually better description. You can use this description. This is an alternative description for this nx. Okay, so this nx possible values of nx can be written in this way, can also be written in this way. The first one that I wrote is simpler, but I wanted to give you both. Okay. So I have not answered the question yet. The question was, what is the joint probability density probability mass function? The joint probability mass function is given by this formula, which is the notation is f n x ij is equal to probability n is equal to I, x is equal to j. Okay, so this is intersection of two events. Okay, so what is n is equal to I comma x is equal to j, which is essentially same as probability of these two events. N is equal to I and x is equal to j is happening at the same time. So this is intersection. Okay, so how do we figure this out? So f n x I j, by the way, so this is the definition of any probability mass function in general. And this f subscript nx ij is the notation. It is the notation for the joint probability mass function. Like we have the notation for the density functions, right? So fxx, fyy, and those kind of things. The joint probability mass functions, since there are two variables, you will write two variables in the denominator. Okay. So this is given by a probability n is equal to y, x is equal to z, which I can write as probability x is equal to j, given n is equal to y times probability n is equal to y. Okay. So if it is given that n is equal to y, which means you roll a dice and the outcome is face value is I. So I could be anything from 1 to 6. Maybe I is 5. So you know that the outcome of the dice roll is 5. But then you were asking, what is the probability that you get j many hits? Okay. Essentially, you were asking that you got 5, you are tossing the coin 5 many times, and what is the probability that you get j many hits? And as you have done this several times, this means I choose j, p to the power j, 1 minus p to the power I minus j. And the last one, probability n is equal to I, is 1 over 6. And you put the range of the mass function. So I can be from 1 to 6, and j is from I, j is from 0 to I. The number of hits that you can get is at most I and at least 0. So this part is essentially following from the part I wrote here, that n is from 1 to 6 and x, the values of x is from 0 to n. So this is what I wrote here. And the value of n, which is I, so I is from 1 to 6 and j can be at most the value of n, which is I here. Equivalently, which is not necessary, but you can write this as also that 0 less than equal to j less than equal to 6, and max 1j less than equal to I less than equal to 6. So you can alternatively write it in that way also, but it is not necessary. This one looks easier. Using the notation p here, probability of getting hit is p. So let me include that here. In this coin, probability of getting hit probability of getting hit is P. All right, so that's it. So we got the joint probability mass function. Okay, so what you see here is simply the joint PMF. Okay, so why is it called joint PMF? Because I'm looking at X and Y, N with I and J jointly at the same time. So this is the joint probability mass function. Okay. So does anyone have any question about this process so far? Um, Let me note down some properties. Um, One-dimensional probability mass functions. Okay. Here we also have, if you have a joint probability mass function, then summation, you have double summation, f n, so okay, we have two random variables x and y, fxy, ij, and you take sum over I and sum over j is going to be equal to 1. You can do the sum in other direction also. Fxy, ij, say this is I, that is j, is going to be 1. Recall that in one-dimensional probability mass function, so in one dimension, you have summation of fx k, sum over all possible values of k gives you 1. This is one-dimensional probability mass function. And this is two-dimensional probability mass function. You take double sum. You first take sum over one index and the next index. If you take sum over all possible indices, you get 1. Okay. For example, in our case, in example 1, we would have summation f n x ij, f n x ij, and we take sum over I first. Let's say I is equal to 1 to 6, and then j is going from 0 to I, so 0 to I. This sum would be equal to 1. Okay, the total probability is equal to 1. Okay, so essentially, essentially what we are doing now is copy of what we did last week, except we have two random variables now, and all the properties will be actually similar. The sum of total probability is 1, and so on. If you have any question, you can stop me any point of time. Along the same line, there is a concept called marginal probability mass functions. What is the marginal probability mass function? Let x and y be two discrete random variables. The marginal probability mass functions of x and y. And y are given by respectively um, so the marginal probability mass function of x is fxi, that is summation of the joint probability mass function fxy ij, and the sum is taken over j. And similarly, for the marginal probability mass function of y, fy j is going to be summation f x y ij, so sum of the joint probability mass function across the other index, which is I. So in our case, for example,
Sir, could you please discuss the marginal PMFs? I'm not getting that one.
okay, so I'm discussing it. I'm giving an example now. So marginal PMFs are obtained from a joint probability mass function. So if you know the joint probability mass function, so joint probability mass functions are indexed by two indices, okay, I and j. There are two random variables. If you integrate out, or if you sum over one random variable, what you get is going to be the marginal of the other random variable. So essentially, it is basically like a row sum and column sum of tables. It's a very simple concept. So in this picture again, if I sum across this horizontal line, okay, so if I take sum across this horizontal line, I would get marginals of fx j. And if I sum across the vertical line, I would get the marginal of n, fn I. Okay, so for example, if I do this sum, so if I sum of all the probabilities which are located on these dots, this would give me fx 1. Okay, if I sum of all the probabilities along this line, this should give me fx 4. If I sum of all the probabilities along this vertical line, this should give me fn so fn 5. So basically the point is that for each I and j, so I and j's are falling in this region, right? So this point is like I is 4, j is 2. This point is I is 6, j is 2. This is I is 6, j is 3. So with each of these points, a probability is associated. Okay, with each of these points, this is actually the whole thing is actually going to be a three-dimensional graph. The domain is this, and there is going to be a vertical line with this height of the probabilities. So each of the points in the dots, these probabilities are associated. Okay, so if I ask what is the probability associated with this point, which is 4, 3. Okay, um, so this is 4, 3 or 2. Yeah, this is 4, 2. If I ask what is the probability associated with this one 4, 2. So you plug in I is equal to 4, j is equal to 2. It will be 4 choose 2, p square, 1 minus p square, 1 over 6. And so on. For each of these points, a probability is associated. Now, if I add up all the probabilities along a horizontal line, like here, if I add up all the probabilities along this horizontal line, I will get the probability of x is equal to 4. If I add up all the probabilities along a vertical line, like this one I said, along the vertical line of 5, I'll get the probability that n is equal to 5. So, right. So I think that I wrote here, this is nothing but probability that n is equal to 5. This is the probability that x is equal to 4. Okay. So essentially, the joint probability gives you information about two variables together. But if you want to extract information about a single variable, so this is important clause. If you want to extract information about a single variable, or if you want to find the probability mass function of any single variable, what you do, you take the sum across the other variable. This is the whole idea. Okay. So in example 1, that if n I is going to be summation f x, sorry, excuse me, n x I j, we take the sum over j, and similarly if xj is going to be summation I f n x ij. Okay, the first one is valid for any j, so any I between 1 and 6. Second one is valid for any j between 0 and 6. So this is the concept of marginal distribution. So you want to extract the probability mass function of a single variable from a joint distribution. You take the sum over only one index. By mistake, if you take sum over both the indices, like here, if you take the by mistake, if you take sum over both the indices, you will get one. You are not going to get the marginal distribution. Okay. And this also implies one thing here. As I said, if you take sum over both indices, you get one, which means if you take sum over I, f n I, this will eventually boil down to sum over I, and then sum over j f n x I j, which is 1. Now, if you think about this, this is very consistent with all the previous lecture. It is saying that if you take sum of this f and I, this is the probability mass function of n only. The sum is going to be 1. It is also telling you that sum of the joint probability mass function is 1, and so on. So I'm not doing the calculations here, but for n, if you do this calculation in our example, this is actually going to be 1 over 6. Now, if nx ij, so if nx ij is given by this formula, if nx ij is given by this formula, if you fix any I, so if you fix the I, that's I is equal to 5, and you take sum over all possible j, you take sum over all possible j, you are going to get 1 over 6 as answer. So you can double check by yourself. I'm not doing it, but you will get 1 over 6 as the answer. Along the same line, there is something called conditional PMF. Which is again nothing but the concept of conditional probability. Okay. Again, we have two random variables x and y. Let x, y be two jointly distributed. The conditional probability mass function, the of x given y is given by, and you already know this answer from our previous lectures, that conditional probability mass function of x given y, say I given j is going to be f x y ij, which is the joint probability mass function, divided by the marginal of j, which is marginal of y, fn, fyj. Okay, so essentially what I wrote in above is nothing but the fact that probability x is equal to y given y is equal to j equal to probability x is equal to y intersection with y is equal to j divided by uh, probability y is equal to j. But you already know this from like Bayes theorem lecture. When I was talking about Bayes theorem and so on, you already know about this formula. So the formula that I wrote here is kind of repackaging of what we have learned in the week before the previous week. It's essentially conditional probability formula. Okay. So for example, in example 1, if I ask this question, say if say x given n 3 given 5. So which means what is the probability that x is equal to 3 given that n is equal to 5? So this should be if x n 3 5 divided by f n 5. Okay, and these all information are already available to you. So if x n 3 5 is 5 choose 3 p cube 1 minus p square times 1 over 6, and f n 5 is 1 over 6. All of this information are actually from this joint distribution here. So I get f n x 3 5 is from this information there, and f n 5 I got the information from here. F n 5 all for all I is 1 over 6. So you get this as 5 choose 3 p cube 1 minus p square. Essentially, the question is, if it is given that the outcome of the dice roll is 5, what is the probability that you get 3 hits from the coin toss? This, that kind of thing. So conditional probability mass function is essentially repackaging of what we had week before last week, which is the conditional probability. And along the same line, we have the independent random variables. So two random variables, two discrete random variables. Called independent. If again the same logic here, if the joint probability mass function is the product of marginal probability mass function. So if the joint EMF marginal PMFs.
Sir, what you are writing, it is not visible. The screen is being so larger.
It's not visible.
Then now you please make the screen somewhat smaller.
Oh, okay. Let's see. So.
No, sir, not now. Please not now.
Okay, it's fine now, right?
No, sir.
Yes, fine.
Sir, somewhat is if you
Sir,
decrease.
it is fine, sir. It is fine.
So maybe it is your device's screen problem, I think. So essentially what I'm saying here that two random variables are independent if you calculate the marginals and if you take the product of the marginals, uh, fxi, fyj. So you calculate the marginals and you take the product. If this is same as the joint probability mass function, then we call those two random variables are independent. But if it is not same for all I and j, those random variables are not independent. It is again the same thing of the independence from the previous lectures, that the probability of A B is equal to probability A times probability B. The same logic here. And one final remark that I would like to mention here is, so for example here, so when you are calculating the marginals, say fxj, which is summation of the other variable index of I, this can also be done in the following way, which is if x given n j given I times probability, not probability, okay, I do not write probability here, times f n I sum of I. Why is that? This is very simple. This is actually a law of probability. You can actually see it from here. That if xy ij is same as if x given I given j times fyj. That's what I wrote here. So I had if nx ij, which can be written as if xn j given I if n. So basically the point is that what I said today is nothing new. It's essentially conditional probability and law of probability and repackaged in a different format. Okay, so that's all I had today to discuss. Next time I will give some more examples of this. I have this 2 hours lecture about this conditional mass function, and I'll also do the continuous part, which is joint PDF and marginal PDF, conditional PDF, and so on. Okay, so this is the end of today's lecture, and we can go to that as usual, that assignment tab, and we take that assignment. And once you are done with this survey, we may read the session.